Hi, I'm Chris with Sanderson Test Prep, and in this video we're going to take a look at an optimization question dealing with fencing. We've done a couple other examples similar to this, but this one's a little bit unique because we're going to have an outer rectangle with a piece of fencing right down the middle. So let's take a look at this sample question. A 216 meter squared rectangular patch is to be enclosed by a fence and divided into two equal parts by another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fencing material needed? Okay, so first of all, we want to see if we can draw out the situation that we're seeing here. So we have a rectangle, and we've got the rectangle divided into two equal parts by another piece of fencing down the middle. So that's the unique part of this, because it's not just a perimeter and area situation, but we also have this additional piece of fencing down the middle that complicates things a little bit. So let's call this dimension X, and we can call this dimension Y. And for the area, so they give us this area of 216. So that is going to be part of our constraint equation because we have a set value there. So we know that the area of a rectangle is X times Y, and that is going to be equal to 216. And then for our total amount of fencing, so in order to figure out the dimensions of everything, we need to try to minimize the total. So that's the next part. They want the smallest, that's our minimum value, the smallest total length of fencing. So let's come up with an equation for total length of fencing. And here, this would be 3x plus 2y. But based on this area equation, we can actually, let me move that down a little bit, because here for the area equation, we can say that y is equal to 216 over x, and then use a little bit of substitution in place of y so that we can have our total length of fencing in terms of just one variable. So here we would have 3x plus 2 times 216 divided by x. And this would simplify to our total length of fencing is 3x plus 432. You could write it over x, but since we are going to have to take the derivative, since this is the equation that they're asking for the minimum for, I would recommend writing it out as x to the negative 1, because it's going to be a little bit easier for us to apply power rule when we see it written out that way. So now let's find the derivative of our equation for t. So t prime is going to be 3 minus 432 x to the negative 2. And remember, this is the equation that to find the minimum, we're going to want to set that equal to 0, because at that minimum value, the derivative, or the slope of your tangent, if you picture it graphically, that derivative function or that slope of that tangent would be horizontal at that minimum. So when we're looking for the minimum, we're setting that derivative equal to 0. And here, when we do that, we get 0 equals 3 minus 432 over x squared. We can subtract 3 from both sides. Negative 3 equals negative 432 over x squared. Multiply by the x squared. Negative 3x squared equals negative 432. Let me slide this up a little bit. Divide both sides by negative 3. X squared equals 144. And x would equal 12. And now we can take that dimension back to our original figure, and we can say that if x equals 12, then we know that each of these pieces would be 12. And then to solve for y, we can plug that back into our area function here. And so for this last step, we're going to take this area function, plug in a 12 for x, and here we have 12y equals 216. And we solve for y, we get y equals 18. So the dimensions of these longer sides will be 18. And now we have the answer to the question for the dimensions for the outer rectangle. And we could also answer any other questions that were asked in a question like this. So if they had asked you to come up with what that total amount of fencing would be, some questions like this would incorporate cost. What's the least expensive way to build this rectangular enclosure with these dimensions and so forth. So as long as you have all those dimensions, then you're going to be in good shape. And as a quick recap, to get those dimensions, we find our constraint function is the one that has the constant value in the problem. And then our objective function, in this case, total, that's what they're asking for. That's really what the question's asking. And that's the function that you're going to want to take the first derivative of, as we did here, and then set that equal to 0. For more, please check out our other videos on optimization. And